morning students, myself Suma from the Department of Mathematics. So in the first session, I'll just discuss about the syllabus part, the chapters that has been allotted to you all from the PUC board. There are 13 chapters that has been allotted. So we'll just discuss these chapters one by one. The first chapter is sets. The first chapter is sets. Second chapter is relation and functions. Relations and functions. The third chapter being sequences and series. Fourth chapter being permutation and combination. And the fifth chapter will be limits and derivatives. Sixth chapter will be probability. Seventh chapter will be statistics. Eighth chapter will be straight lines. Ninth chapter will be principle of mathematical induction. Principle of mathematical induction. 10th chapter will be complex number. Complex number. The next chapter will be sets, relation and functions, sequence and series, permutation and combination, limits and derivatives, probability, statistics, straight lines, principle of mathematical induction. The next chapter will be linear inequalities. The 12th chapter being introduction to 3D geometry. Introduction to 3D geometry, and the 13th chapter will be trigonometric functions. Chapter being trigonometric functions. There are few chapters like mathematical reasoning, binomial theorem, which has been in the deleted portion for the academic year 2020-21. So this academic year we shall be teaching 13 chapters. In case of any clarifications with regards to reductions of the syllabus part or the chapters, I will let you all know in the further classes. So to summarize quickly, we have 13 chapters that has been allotted in the first PUC mathematics syllabus. We shall discuss about each chapter, the definition part, the introduction of the chapter, the synopsis of the chapter, and so on, as and when we take the classes. And when we start with every new chapter, I'll just be telling you all about the weightage of each chapter that is being allotted in the question paper. So you all can take down when we start off with the actual syllabus. So we have these many chapters: sets, relation and functions, sequence and series, permutation and combination, limits and derivatives, probability, statistics, straight lines, principle of mathematical induction, complex number, linear inequalities, introduction to 3D geometry, and trigonometric functions. So first and foremost, let me start off with one chapter, that is principle of mathematical induction. Principle of mathematical induction. Now, let us discuss what is induction. The word induction means it is the generalization from the facts or cases. In algebra or in other discipline of mathematics, there are some standard results or statements that has been formulated in terms of n, where n is a small positive integer. So, to prove these standard results or statements, we will be using a specific technique, and this technique is known as principle of mathematical induction. There are some 3 or 4 working rules to be followed in this chapter, which is applied for the problems. So I'll just discuss about the working rule now. The first step in the working rule step 1, we will denote the given statement as P of n. When I say statement, the question itself, we will denote it as P of n, or we will call the question it as P of n. So step number 1, denote the given statement, as P of n. Step number 2, assume the given statement is true for n equal to 1. Step number 2, assume the given statement is true for n equal to 1. That will be step number 2. Then step number 3, assume the given statement is true for n is equal to k. Assume the given statement is true for n is equal to k. And step number 4, that is the last step, will be using step number 3, we shall prove that the given statement is true for n equal to k plus 1. Using step number 3, we are proving that the given statement is true for n equal to 1. Using step 3, we shall prove the given statement is true for n is equal to k plus 1. You need to know the important points in these 4 steps. Step number 1, denote the given statement as P of n. So what is the first step? We will denote it as P of n. Step number 2, assume the given statement is true for what? N is equal to 1. Similarly, step number 3, assume the given statement is true for n equal to k. And step number 4, which is very important, using step number 3, we shall prove that the given statement is true for n equal to k plus 1. Once these steps are satisfied for the given problem, we'll say that hence by the principle of mathematical induction, the given statement is true for all n belongs to n. Clear? So, keeping this in mind, we shall start solving the problems. The first 3 problems are standard problems. Those are the standard results which we shall be using it in other chapters as well. So, keeping this in mind, we shall start off with the problems. The first problem is, using PMI, prove that 1 plus 2 plus 3 plus etc. plus n is equal to n into n plus 1 by 2. So as discussed earlier, what is the first step? We shall denote the given statement as P of n. So first step, let P of n is equal to 1 plus 2 plus 3 plus etc plus n is equal to n into n plus 1 by 2. We have denoted the given statement as P of n. What is the second step? Assume that the given statement is true for n equal to 1, which means what? Wherever there is n on the LHS and RHS, we are supposed to put the value of n as equal to 1 and check whether LHS is equal to RHS. So, for n is equal to 1. Here, what is the nth term on the LHS? When you look at the question, the nth term on the LHS is nothing but n. So, wherever there is n, what have we assumed? For n is equal to 1. So, in place of n, you will put 1. This is all about LHS. Moving on to the RHS part. Which is the nth term in the RHS? This is the question, and what is the nth term in the RHS? N into n plus 1 by 2. N into n plus 1 whole thing divided by 2. So in place of n, what do we put? 1. So what does it sum up to? 1 into 1 plus 1 divided by 2. Both get cancelled. The answer is 1. Now, can I say LHS is equal to RHS? We've got the same answer. Hence, we can come to a conclusion that LHS is equal to RHS. So here, LHS is equal to RHS. Therefore, the given statement is true for n equal to 1. Therefore, the given statement is true for n equal to 1. Is that clear? Now, next step, for n is equal to k. For n equal to k. When you observe step 2, in place of n, what do we write? 1. So when you observe step 3, in place of n, what do we write? In place of n, in the question we write as n. So the given question becomes 1 plus 2 plus 3 etc plus k is equal to k into k plus 1 whole thing divided by 2. In place of n, we wrote k on the LHS and RHS. Therefore, the given statement is true for n is equal to k. The given statement is true for n equal to k. Now, moving on to the last step of the problem. In the working rule, it is mentioned using step 3, that is for n equal to k, we shall prove that the given statement is true for n equal to k plus 1. So, here for n is equal to k plus 1. Now, kindly observe, for n is equal to k plus 1th step, what do? We will add the next term on both the sides. We will add the next term on both the sides. Now, observe the question. After 1, which number do we have? 2. After 2, which number do we have? 3. So, after 3, which number will be here? 4. And after 4, it will be 5 and so on. Which means what? To get the next consecutive number, we are adding 1 for each term. After 1, only when you add 1, you get 2. And for this 2, if you add 1, you get 3. And for this 3, if you add 1, you will get 4 and so on. So, for each term, you are adding 1. What is the last term of LHS? N. So, which will be the next term of n? Which number to be added for n to get the next term? 1. When you add 1, the next term will be n plus 1. Once again I repeat, observe the given question here. 1, after that I have 2, after 2 I have 3, and so on. To get 2, which number I should add 1? The number 1. To get 3, which number I should add 2 plus 2? 1. Which will be the next number after 3? It will be 4. To get 4, which number I have to add for plus 3? It is nothing but 1, which means to get the next consecutive numbers, we are supposed to add 1. So what is the last term of the LHS here? N. So to get the next term, which number am I supposed to add? Plus 1 again. So what will be the next term? It will be n plus 1. Moving on. What is the last step of the working rule indicates? Using step 3, which means I have to add the next term of k here, because this is step 3. We are using this step and we are adding it. So to get the next term, I will add plus 1. So when I add plus 1, what is the next term of k here? We get k plus 1. So for n is equal to k plus 1, add the next term, k plus 1 on both the sides. So what does the given problem become now? 1, that is using step 3. 1 plus 2 plus 3, etc., etc., plus. What do I have here? K. Which is the next term I am supposed to add on both the side? Both the side means LHS and RHS. So what do I get? K plus 1, which is equal to, what is RHS? K into k plus 1 divided by 2 plus k plus 1. Observe here, I have added k plus 1, that is the next term on LHS, as well as I have added k plus 1, that is the next term on RHS. I have added the next term on both the sides, LHS and RHS. Is that clear now? Next. Simplification part. Consider RHS. What is here? RHS part? K into k plus 1 into, okay, k into k plus 1 divided by 2 plus k plus 1. K plus 1. The same step have been written here. K into k plus 1 divided by 2 plus k plus 1. Now, I need to take LCM and simplify, cross multiply. What do I have here? K into k plus 1 plus, when you cross multiply, what do we get? 2 times k plus 1. When you cross multiply, what do we get? 2 times k plus 1 whole thing divided by 2. Complete thing divided by 2. When you observe the numerator, which term is common in the numerator? K plus 1. So I will be taking k plus 1 outside the bracket as the common factor, and which term will be left out here? K plus 2. So this is k plus 1 is a common factor taken out. Which are the terms left now? K plus 2, complete thing divided by 2. Complete thing divided by 2. Now, most importantly, now what we are supposed to do is, each term of k has to be represented in terms of k plus 1. Each term of k must be represented in terms of k plus 1. When you observe k here, can I say k is represented in terms of k plus 1? Yes. But when I see here the term k is represented in terms of what? K plus 2. I need to represent every term of k in terms of k plus 1. So what do I do? The term k here is already in terms of k plus 1. What do I have here? K in terms of what? I have here in terms of k plus 2. But I need to represent it in terms of k plus 1. So what do I do? K will be in terms of k plus 1 plus, what number gives me 2? 1 plus, what number gives me 2? 1 plus which number? That is nothing but 1. Complete thing divided by 2. Now, The last working rule, it states that for n is equal to k plus 1 or k plus 1 is equal to n. So what is k plus 1 equal to now? N. What is k plus 1 equal to? N. What is the term left out here? N plus 1. N plus 1. That is, we have assumed k plus 1 equal to n. So if I consider this term to be as n, I can rewrite this as n plus 1 whole thing divided by 2, which is equal to RHS. Which is equal to RHS. Therefore, what is the statement we are supposed to write here? Therefore, the given statement is true for n equal to k plus 1. Therefore, the given statement is true for n equal to k plus 1. So what will be the final conclusion? Hence, by the principle of mathematical induction, P of n is true for all n belongs to n. Final conclusion will be, hence, by the principle of mathematical induction, the given statement is true for all n belongs to n. Hence, by PMI, that is principle of mathematical induction, the given statement, or you can write P of n, because we have denoted the given statement as P of n. P of n is true for all n belongs to n. Is true for all n belongs to n. This is about the first problem. Quickly to summarize, denote the given statement as P of n. Assume the given statement is true for n equal to 1. Assume the given statement is true for n equal to k. By using the statement n equal to k, we are supposed to prove that the given statement is true for n equal to k plus 1. Clear? Next. Moving on to the second problem. So what does the second problem states? That using PMI, prove that, that is principle of mathematical induction, prove that 1 square plus 2 square plus 3 square plus etc plus n square is equal to n into n plus 1 by 2. N into n plus 1 by 2. The second question states that using PMI, prove that 1 square plus 2 square plus 3 square etc plus n square is equal to n into n plus 1 into 2n plus 1 whole thing divided by 6. Whole thing divided by 6. Now, what is the first working rule? Step number 1. We shall denote the given statement as P of n. So, let P of n is equal to, let P of n is equal to 1 square plus 2 square plus 3 square plus n square is equal to n into n plus 1 into 2n plus 1 whole thing divided by 6. This is the first step. What is the next step? Assume that the given statement is true for n equal to 1. Implies what? Wherever there is n on the LHS, you are supposed to put the value of 1. Similarly, wherever there is n on the RHS, you are supposed to substitute the value of n is equal to 1 and check whether LHS is equal to RHS. That is all about step number 2. I repeat, for n is equal to 1, assume that the given statement is true for n equal to 1. Wherever there is n on the LHS, you are supposed to put 1. Wherever there is n on the RHS, you are supposed to put substitute the value of n is equal to 1 and check whether the given statement is true for n equal to 1. We say the given statement is true for n equal to 1 only when LHS is equal to RHS. So, first step here, second step, for n equal to 1, consider LHS. What is LHS? What is the nth term here? N square. So, in place of n square, what am I supposed to put? 1 square, because n is equal to 1. And what is 1 square equal to? 1 itself. We shall check for RHS now. This is the RHS part. What is in the RHS? N into n plus 1 into 2n plus 1 divided by 6. In place of n, what do you put? 1. In place of n, which value you will substitute? 1. What does 1 plus 1 sum up to? 2. Similarly, in place of n, which value you will substitute? 1. 2 into 1, 2. 2 plus 1, 3. In place of n, you will assume the value of n to be 1. So, 2 1s are 2. 2 plus 1 will be 3. Complete thing divided by 6. 3 2s are 6, 6 1s are 6. Will cancel out and this will sum up to 1. So, observe, can I say LHS is equal to RHS here? Yes. Therefore, the given statement is true for n equal to 1. You are supposed to write here, therefore, the given statement is true for n equal to 1. As I explained you all in the first problem, you need to rewrite the same statement. Therefore, the given statement is true for n equal to 1. Clear? Moving on to the next step. For n is equal to k. For n is equal to k. What does it mean for n is equal to k? Wherever there is n in the question, you are supposed to replace it by k on both the side, LHS and RHS. So, rewriting this question, what do we get again? 1 square plus 2 square plus etc. n square. N takes the value k. What does n takes the value here? K. So, in place of n square, which term you will write? K square equal to k into k plus 1 into 2k plus 1, complete thing divided by 6. So, what is the conclusion you write here? Therefore, the given statement is true for n equal to k. This is the conclusion you write here. Therefore, the given statement is true for n equal to k. Similarly, for n equal to 1 in the previous step. Now, what is the last step of the problem? We are supposed to prove the given statement is true for n equal to k plus 1. For n is equal to k plus 1. In this step, using step number 3, we are supposed to prove the given statement is true for n equal to k plus 1. In this step, what do? We will add the next term of k on both the sides. We will add the next term on both the sides. Observe this step here. 1 square I have. After 1 square, what do I have? 2 square. That is, I have added 1 for the first term to get 2. After 2 square, the third term will be 3 square. After 3 square, it will be 4 square and so on. So, to get the next term, what do? I will add 1. And what is the last term of the LHS? K square. Which number I should add? Plus 1. After me adding plus 1, what will be the next term I get? It is k plus 1 whole square. So, here add the next term. NT, I'll just write in short form, it's the next term. Add the next term, k plus 1 whole square on both the sides. So, what does the given question becomes now? 1 square plus 2 square etc. plus k square plus, which is the next term to be added on LHS and RHS? K plus 1 whole square. So, which term shall I add here? K plus 1 whole square equal to, what is in the RHS? K into K plus 1 into 2n plus 1, complete thing divided by 6 plus, which is the term I have to add on the RHS as well? K plus 1 whole square. K plus 1 whole square. So observe here, I have added the next term on the LHS as well as I have added the next term on the RHS. Now, further simplifying, I will simplify the RHS part now. What is RHS? K into K plus 1 into, this is 2K. 2K plus 1 whole thing divided by 6 plus K plus 1 whole square. Previous problem, what we did do? We took the LCM, simplified, represented each term of K in terms of K plus 1. The same steps we shall follow here. This is K into K plus 1 into 2K plus 1. When you multiply, cross multiply, what do you get? 6 times the K plus 1 whole square. 6 times K plus 1 whole square, whole thing divided by 6. Clear everybody? 6 times the K plus 1 whole square divided by 6. Observe the numerator. Which term is common in the numerator now? The term K plus 1. So I shall take out K plus 1 as a common factor. When you remove K plus 1 as the common factor, which is the term that is left out in the numerator? K into K plus 1 is taken out as a common factor, which is the term that is left out? 2K plus 1 plus 6 times K plus 1 whole square I have here. K plus 1 I have taken out, which is the term that remains as it is? K plus 1 itself. K plus 1 whole thing divided by 6. Now, this is K plus 1. Simplifying further, K into 2K, 2K square plus K plus 6K plus 6, complete thing divided by 6. Complete thing divided by 6. This is again K plus 1. This is 2K square. 6K plus 1K, 7K plus 6. Whole thing divided by 6. 2K square plus 7K plus 6. Now what am I supposed to do? I need to factorize the numerator so as to get the term K, wherein I can represent K in terms of K plus 1. So what do I do now? I will factorize the numerator part, that is 2K square plus 7K plus 6. So factorizing the numerator part in the working column, what do I get? K plus 1 I will rewrite as it is. Now, this is the working column part. 2K square plus 7K plus 6. Factorize. 2K square plus 4K plus 3K plus 6. What is common here? 2K. So I can take 2K as common. What is left out? K plus 2. Similarly, what is common here? 3. What is left out? K plus 2. So I can rewrite this as 2K plus 3 into K plus 2. Numerator 2K square plus 7K plus 6 is factorized, and the reduced term will be 2K plus 3 into K plus 2. So what do I write in place of 2K square plus 7K plus 6? I will rewrite this as 2K plus 3 into K plus 2 whole thing divided by 6. As mentioned earlier, each term of k has to be represented in terms of k plus 1. So when you observe the kth term here, can I say k is represented in terms of k plus 1? Yes. So this is k plus 1 as it is. Now observe here, 2k plus 3. 2k plus 3 has to be represented in terms of k plus 1. Observe k. Is the term k represented in terms of k plus 1? No. So what do I do here? 2k plus 3. I have to represent k in terms of k plus 1. So k I will write as k plus 1 plus 2 into k. I am getting back 2k plus 2 ones are 2. 2 plus what number gives me 3? It is nothing but 1. I'll repeat that. Observe carefully. I have to represent each term of k in terms of k plus 1. So in terms of, I have here k. I have to represent in terms of k plus 1. So what do I write? 2 into k plus 1. Representing k in terms of k plus 1. When you multiply 2 into k, you're getting back 2k plus 2 ones are 2. 2 ones are 2 plus what number gives me 3? It is nothing but 1. So cross check. 2k, 2 into k, 2k plus 2 ones are 2 plus 1, summing up to 3. So 2k plus 3, I can rewrite it as what? 2 into k plus 1 plus 1. This is the first term. Similarly, tell me the second term now. What do I have the second term here? K plus 2. I have to represent k plus 2 as in terms of what? K plus 1. So in place of k, what do I write first? K plus 1. K plus 1 I have, but I'm supposed to get 2. 1 plus what number gives me 2? By adding 1. So k plus 2 can be written as k plus 1 plus 1. K plus 1 plus 1. K plus 1 plus 1. According to the assumption, what is k plus 1 equal to? According to the assumption, what is k plus 1 equal to? N. What is k plus 1 equal to? N. So in place of k plus 1, what do I write? N. N into k plus 1 becomes what? N. So 2n plus 1. What is k plus 1? N. So which is the term that is left out here? N plus 1. Whole thing divided by 6. In the previous step as well, it is whole thing divided by 6. So k plus 1 I have represented in terms of n, because what is n equal to? By using the last step, n is equal to k plus 1. So wherever there is k plus 1, you can write it as n. So k plus 1 is written as n. 2n plus 1 into n plus 1, which is equal to 6, which is nothing but RHS. So what is the final statement you're supposed to write? Therefore, the given statement is true for n equal to k plus 1. Therefore, the given statement is true for n equal to k plus 1, and the final conclusion of the problem will be, hence by the principle of mathematical induction, hence by principle of mathematical induction, you can write PMI, hence by principle of mathematical induction, the given statement is true for all n belongs to n, where n is a positive integer, for all n belongs to n. This is all about the second problem. The working column part, I'll quickly summarize once again. K plus 1 is taken common here. The left out term will be k into 2k plus 1 plus 6 times the k plus 1. You multiply, you get 2k square plus k plus 6k plus 6. 6k plus k will sum up to 7k. So the numerator will be 2k square plus 7k plus 6. You need to factorize the numerator. Once you factorize, 2k square plus 7k plus 6 can be written as 2k plus 3 into k plus 2. So in place of numerator, you will write as 2k plus 3 into k plus 2. As mentioned earlier, each term of k has to be represented in terms of k plus 1. So k is already in terms of k plus 1, no need to write. Here k has to be represented in terms of k plus 1. So in place of k, what do I write? K plus 1. 2 into k, 2k plus 2 ones are 2. 2 plus what number gives me 3? Only when I add 1 to the number 2, I get 3. Similarly, k I'll represent in terms of k plus 1 plus 1. According to the last step, what is n equal to? K plus 1. So wherever there is k plus 1, I will be writing n. And we arrived at RHS. Clear? Next. Moving on to the third problem. What is the third problem? 1 cube plus 2 cube plus 3 cube plus etc. plus n cube is equal to n square into n plus 1 whole square divided by 4. Moving on to the third problem. Using PMI, prove that 1 cube plus 2 cube plus 3 cube plus etc. plus n cube is equal to n square into n plus 1 whole square, complete thing divided by 4. First step, we shall denote the given problem as P of n. So, first step, let P of n is equal to 1 cube plus 2 cube etc. plus n cube is equal to n square into n plus 1 whole square divided by 4. Clear? This is the first step. What is the second step? Assume the given statement is true for n equal to 1. That is, we are proving LHS is equal to RHS by assuming the value of n is equal to 1. So, for n is equal to 1, we shall check what is LHS and we shall also check what is RHS. LHS now. Which is the nth term of LHS? N cube. In place of n cube, which value will you put? 1. 1 cube will sum up to what? 1 itself. Similarly with RHS. What is RHS given here? N square into n plus 1 whole square divided by 4. In place of n, what do you put? 1 square. So this is 1 square into 1 plus 1 whole square divided by 4. What is 1 plus 1 whole square? 2 square. What is 2 square? 4. 4 divided by 4 will sum up to what? 1 itself. So here LHS is equal to RHS. Therefore, the given statement is true for n equal to 1. Therefore, the given statement is true for n equal to 1. N equal to 1. Next, what is the next step? We are assuming the given statement is true for n equal to k. So, for n is equal to k. As mentioned earlier, wherever there is n, you will replace the term n by k. So, what does the given question become now? 1 cube plus 2 cube plus etc. In place of n cube, what do you write? You will write it as k cube equal to k square into k plus 1 whole square divided by 4. What is the conclusion you're supposed to write? The final statement. Therefore, the given statement is true for n equal to k. Next, moving on to the last step of the problem. What is the last step of the problem? using step 3, we shall prove the given statement is true for n equal to k plus 1. Using step 3, we shall prove the given statement is true for n equal to k plus 1. In this step, what did we do in the last two problems? We added the next term on both the sides. When you observe the question, 1 cube will become 2 cube, 2 cube is becoming 3 cube, 3 cube will become 4 cube, and so on, which means you're adding plus 1 for the each next consecutive terms and you're cubing it. So what is the last term here on the LHS? On the LHS, it is k cube. So which number will you add if you have to get the next term? You're supposed to add 1. 1 is becoming 2 by adding 1, 2 will become 3 by adding 1, 3 will become 4 by adding 1, and so on, which means for you to get the next consecutive term, you're consistently adding plus 1. So what is the last term here? K cube. So to get the next term, what should I add? Plus 1. And after adding plus 1, what term do I get? K plus 1. And I'm supposed to cube it according to the question. So add the next term, which is the next term, k plus 1 whole cube on both the sides. Add the next term, k plus 1 whole cube on both the sides. So what does the given question become now after adding k plus 1 whole cube? That is by using step 3, the given problem becomes 1 cube plus 2 cube etc. plus k cube. Which term am I supposed to add? K plus 1 whole cube. K plus 1 whole cube is equal to k square into k plus 1 whole square divided by 4. Which term I am supposed to add now? K plus 1 whole cube. So what is the RHS part now? K square into k plus 1 whole square divided by 4 plus k plus 1 whole cube. Take LCM and simplify. We get k square, cross multiply, k square into k plus 1 whole square. When you cross multiply, what do you get? 4 times k plus 1 whole cube divided by 4. Observe the numerator. Which term is common in the numerator? K plus 1 whole square. Take this k plus 1 whole square as common factor. K plus 1 whole square if you take as common factor, what is left out? K square plus 4 times k plus 1 cube I have here, square I have taken out. So which term remains now? 4 into k plus 1 divided by 4. Among the cube, square is taken out, so only one term remains, that is nothing but k plus 1. Now, in the numerator, I have k square plus 4 into k plus 1. This is k plus 1 whole square, RHS part, into k square plus, start multiplying. 4 into k is what? 4k, plus 4 into 1 is 4. So k square plus 4k plus 4, whole thing divided by 4. When you observe the numerator, k square plus 4k plus 4, can I write the numerator as k plus 2 whole square? In the working column, if you observe k plus 2 whole square, expand this k plus 2 whole square according to a plus b whole square formula. What do I get? A square plus b square plus 2ab. So k square plus 4 plus 4k can be written as what? K plus 2 whole square. So k plus 1 whole square I will rewrite as it is, and k square plus 4k plus 4 can be written as what? K plus 2 whole square, complete thing divided by 4. Each term of k has to be represented in terms of k plus 1. When you observe the first term, k is already in terms of k plus 1, but here k is in terms of k plus 2, wherein I have to represent k in terms of k plus 1. So what do I do? This is k plus 1 whole square. K plus 2 whole square can be written as k plus 1 plus 1 plus what number gives me 2? That is nothing but 1 whole square divided by 4. What have we assumed n equal to? What are we proving for n equal to? K plus 1. So in terms of k plus 1, what do we write? N square into, this can be written as n plus 1 whole square, complete thing divided by 4. K plus 1 is nothing but n, because for n equal to k plus 1, we are proving the given statement. In place of k plus 1 we write n. Here this complete term will become n. This can be written as n plus 1 whole square, whole thing divided by 4, which is equal to RHS. So therefore the given statement is true for n equal to k plus 1, and final conclusion will be hence by PMI, hence by PMI the given statement is true for all n belongs to n. The given statement is true for all n belongs to n. Clear? So we shall end today's session. In my next session, I shall continue the problems of principle of mathematical induction. Thank you very much.